We are Team 11, and this is our final presentation for the analysis and redesign of a floor tile cutter.
The primary use case for our product is tile cutting. Looking at historical data and market demand, the estimated annual production volume is 3 million units. This product is targeting homeowners or contractors who need to cut ceramic tile for a kitchen, bathroom, or other space. The secondary use case for this product is glass cutting. The production volume is less than an estimated 2 million units annually. This product is geared towards glass cutting for small windows, which typically have a larger footprint than tile at a reduced thickness. While similar in their properties, glass carries a greater crack propagation. Next is a fully assembled image of our floor tile cutter CAD model. Here's an exploded view of our CAD model with a full parts breakdown. There are 13 components in total.
Product analysis.
The core function of the tile cutter is to cut tile. It accomplishes this by scoring the tile, controlling and transmitting force. It must break the tile by providing resistance and force. It must hold the tile, positioning and supporting it. Additionally, the tile cutter must assure dependability by enabling maintenance, and convenience by measuring and enabling mobility. Finally, it must enhance the product by reducing fatigue.
Here's our functional component mapping matrix. As shown, most of the components support the primary functions of scoring the tile, breaking the tile by providing upward and downward forces, and supporting the tile during these operations. Some components also support secondary functions such as enabling maintenance, measuring tiles, and other functions. Those are generally seen on the right-hand side of the matrix.
Product family design. On the left, we have the functional differentiation table. Many functions are common for both use cases. For tile cutting only, it must support heavy material and prevent chipping. For glass cutting, it must score with precision and prevent cracking. For glass, it has to support a larger material because glass windows are usually larger than tiles. That brings us to our component commonality table, where all components except for the base, cutter rail, and base supports are common. The base and base support contribute to force transmission and tile support. These functions are critical to customer material choice, which means they have to be modules. The base support is eighth on the BOM in cost and carries a lower impact, allowing for benefits in areas such as bulk discounts and inventory management.
The first module change for the secondary customer is to the base and base support. The base and base support increase in size to handle larger glass panes and can be seen in blue. The second module change is to the cutter rail. Length is increased to control scoring over the longer distances required for larger glass panes and is highlighted with red arrows. The common interface for both of these changes is the front and rear cutter mounting brackets, which are shown in purple.
The common interfaces between the designs are found in the front and rear brackets. The rails seat into the holes identified in blue. The base of the brackets is secured to the base assembly using bolts.
Looking at the current product family assembly diagram, the part variation appears at the beginning with no strategy to prioritize common components. In the diagram for the modified assembly, we enable delayed differentiation to take place by front-loading the common components for an improved result.
Design for assembly.
Design for manual assembly was completed, and the results drove us to select the cutter rails and rail spacers as our module parts. The cutter rails fall into the high cost and high functional importance area of the quad chart, and the rail spacers fall into the high cost but low importance area, making them good redesign candidates. The cutter rails and spacers were combined from two separate parts into one, reducing overall part counts, reducing part variety, and providing a location feature on the spacer end of the rail for install into its mounting bracket. The platform part we selected was the cutter bracket, handle, and handle extension. The cutter bracket falls into the high cost and high functional importance cost bucket, making it ideal for redesign. This redesign involved turning the cutter bracket and handle extension into one piece, reducing part counts, reducing fasteners, and reducing part variety. The handle was redesigned as well, but other requirements for ergonomics drove us to keep it a separate piece. We were able to reduce fasteners here as well. As a result of our platform and module part changes, we were able to reduce our total assembly time from around 285 seconds to around 240 seconds. We also improved our assembly efficiency by around 2%. The overall function of the tile cutter is not affected by these changes, but the manufacturing cost has been reduced.
For our design for automated assembly, our components we selected for the subassembly process under analysis are the cutter bracket, cutter, and force applicator. We selected these components based on our functional component mapping matrix and quad chart for high importance items, as well as items that would be suitable for automated assembly and were less than 100 millimeters in size. For our pre-DFA analysis, the assembly cost was $5.72. In our post-DFA analysis, the assembly cost was $1.63 for an overall delta of $4.09. This slide depicts the updates that were done for our automated assembly for the cutter bracket subassembly. The pre-DFA design is complex for automated assembly, with nuts being installed on the backside and angled loading for the force applicator and cutter with difficult screw alignment. The post-DFA design, we eliminated the need for the nuts with a tapped hole, as well as reduced the need for one screw. There is now tool axis from the top. Locating features were added for the cutter to be installed up-down on a pin, as well as locating features for the force applicator and screw. The new subassembly can be completely assembled in the up-down direction with no reorientation required.
We will now cover process selection and design for manufacturing. The cutter rails and spacers were chosen as our module parts for redesign and were combined into a single component. The main area that contributed to the function component mapping matrix is the smaller 20mm diameter that interfaces with the front and rear brackets for assembly, and the slide area that interacts with the rail bracket. This area corresponds to the transmit force control score functions. A tolerance of 0.1 millimeters for the diameters was set. Looking at the potential processes, only machining was highlighted. Section thickness prevented sand casting from being used. For this batch size and the geometry, machining was the best option moving forward.
In order to calculate the design for machining costs for our cutter rail, we used a slightly different method than what was taught in class. Instead of using a cost per mass estimate for our stock, we obtained a quote from a real company for aluminum round tubes that had similar dimensions as our cutter rail. Each tube was 288 inches long, which meant that 11 cutter rails could be made per tube. 2 cutter rails are needed per unit, and 3 million units was our production volume, which means that we had to order 545,000 tubes for a cost of $32.2 million. To optimize for machining, first we increased the outer diameter by 0.4 millimeters to match the outer diameter of the tube. This demonstrates DFMC 2 and 3, use standard stocks and standard dimensions. For DFMC 5, avoid long narrow holes, we eliminated the need for a drilling operation by decreasing the inner diameter of our tube by 2.3 millimeters to match the inner diameter of the stock. Lastly, we increased the length of the thicker portion of the end of the rail to reduce a machining operation. In total, this reduced our cost from $16.35 to $15.37.
Moving on to the cutter bracket, for the redesign part, the main features that interact with other components are the holes and the overall width. The through holes have a tolerance of 0.2 millimeters, and they're related to the transmit force function on the function component mapping matrix. For the width, we have a tolerance of 0.15, and it's there to prevent any swaying or rotation. Because the threaded holes have a tight tolerance, they will have to go through a secondary machining process. The primary manufacturing process will be die casting, as per the figure below, and the secondary manufacturing process will be the machining, which is only used for the holes and for tapping for the threaded bolts.
The second component that we analyzed under design for manufacturing is the bracket handle. Initially, it had many non-uniformities for wall thickness, contained sharp corners and edges, it failed to incorporate draft angles, and in general had a lot of excess material in the design, which was causing a long cooling cycle during the die casting process. By altering the design, we were able to greatly reduce the wall thickness by about 15 millimeters for most areas of the component. This also created a near uniform wall thickness throughout the part, which significantly reduced cooling time and subsequently improved the material cost and operating cost. Additionally, draft angles and fillets were added to help with smoother part ejection, tool longevity, and structural integrity of the bracket handle.
Product service systems. So from a sales and service point of view, we'd like to launch a mobile and web app for any common replacement parts, such as a cutter, the base support, which improves customer experience. We also want to add more customizable cutter assemblies, which improves the utility of the product. Then from an environmental and distribution point of view, we're going to reduce packaging by doing bulk shipments, and we'd have an open box product in stores so that we use less packaging and have a better impact on the environment.
For overall conclusions for our DFA improvements for manual assembly, we had a 44-second improvement in the overall cycle time, and our assembly efficiency improved by almost 2%. For our automated assembly proposal, we had a $4.09 assembly cost reduction. And then for our DFM improvements for our handle assembly, we had a 62-cent savings. And then for our rail assembly, we reduced the cycle time by 27 seconds by reducing the machining time. For our critiques, additional cost analysis is required to reduce some of our high-cost components further. There's potential to add the cutter rail bracket as part of our die-cast handle subassembly to reduce parts further. And then some additional analysis or new approaches that could be done would be to modify the base plate for POA studs for easier bracket assembly in order to reduce the screws and nuts further, and to analyze additional automated subassemblies for additional lower cost for the overall assembly.